Hey all, this is Derek in section 6.4, simplifying roots. And so let's start off with the definition. So if x is a non-negative real number, then the expression square root x is called the positive square root of x, and is such that the square root of x squared is x. So what this is saying is if I have the square root of, say, the square root of 5 squared, the square and the root undo each other, and we just get 5. Another way of thinking about that is if I do the square first, that's like square root of 25. So square root of 25 is asking, which is more the word definition here, what number do I multiply by itself to get 25? And that would be 5. And the key here at the positive square root is on the idea of what number do I multiply by itself. Negative 5 times negative 5 also makes 25. So that's why we're being careful to define this as the positive square root is the one that we're looking for. I made a list here of the perfect squares just to reference them. You'll see a little bit later in the section that could be helpful. But for now, let me go on to some examples. And so the square root of 4 is asking, what do I multiply by itself to make 4? And that would be 2. Another way of thinking of a square root is a square root is quite literally the side of a square. So if I have a square that's area 4, what the square root is the length of each of those sides, or 2 times 2 makes area 4. This one is the negative of root 4, which just means it'll be the negative of square root 4 is still 2, so it's negative 2. And then for that negative 4 underneath, remember we're saying what times what would make negative 4? There isn't anything that times itself makes negative 4. And so this one is a DNE, and it turns out it can have what's called imaginary solutions, but that's something that we would look at next quarter, not in this course. This next one, root 17 times root 17, that kind of goes back to our definition there, which is that is root 17 squared, which is just 17. So anytime we see a root times itself, the roots are squared, it clears. This one is just a couple of simple square roots. So square root of 81 would be 9, because 9 times 9 is 81. Square root of 4 makes 2, and now I can simplify. And 9 minus 2 would make 7, and that one I meant to delete, so ignore that. Okay, for these next ones, we are still simplifying, so we're just going to go 2 plus, and then what times what makes 64, so that would be 8 over 5, and now I can simplify this. So 2 plus 8 would be 10 over 5, or 2. For this one, we'll leave that 21 alone for a second, minus 5. Square root of 9, that's going to make a times 3 right there, over 3. Careful not to cancel those 3's. You could cancel both places, but probably better to just do this instead. Make that a 15 over 3. And then 21 minus 15, we'll finish putting together our numerator, and that will make 6 over 3, or 2. These next couple are just kind of getting you introduced to your calculator. So this is give a decimal approximation round to the thousandth. So this is what's called an exact solution. When we have that radical notation going on, that is the exact value. We're saying whatever number that we multiply by itself to make 2, that's what this root 2 is representing. And that number is like 1.41, but it goes on forever. It's irrational, like pi, it never repeats. So this is the exact form. Anytime we show it as a decimal, that's our approximation. So to put these in the calculator, it will really depend on your calculator, but this is basically just saying 6 times, on this one it happens to be a root button right there, and 2, and then close out your parenthesis, and they're rounding to the thousandths, so we'll go to 3 places. So that would be 8.485. And then this one, we're going negative 5. So for this calculator, that would be here, negative 5 minus 3, and then times root 7, and close parenthesis. As that is negative 12.937 to 3 places. Okay, and then last up is simplifying expressions involving radicals, and we're going to pick up property 1 for radicals here. And this basically says if I have a couple of things multiplying under a radical, if it is helpful, I can think of that as 2 separate radicals. And I will show you where that is sometimes helpful. So this time we got the square root of 63. So square root of 64 would be 8. Square root of 49 would be 7. And so whatever this thing is, it's not one of the nice numbers. So this is going to be something that's going to have a root left in it. So either it's just going to stay square root 63, or we'll be able to break it down a little bit, but we're still going to have a square root in it because it's not a perfect square. So here's where we start looking at this list of squares. And what we want to do is try to find one of these squares, well, the biggest square, I guess, that divides into 63. And I have 1 squared on here, not so helpful because 1 squared is 1, so that one doesn't really count for this, but I use this for factoring as well, and it works there. So 4 doesn't go into 63, 9 does go into 63, so that is useful. So I can think of 63 as 9 times 7. And then once I've done that, now I can use this property that says that's the same thing as the square root of 9 times the square root of 7. And then what's square root of 9? That would be 3 square root 7. And then that's the exact form, so we don't want to change that to a decimal or anything. That's what we're looking for right there. So that's the idea of simplifying these radicals, is that we are looking to see if there's any perfect squares that are basically hiding in here. And if so, can we simplify those out as a coefficient? So 175, big number, but if you look at your list of squares, hopefully 25 jumps out as something that's going to divide into 175. So that would be 25 times 7. And notice for me, I'm writing the perfect square first because I'm kind of thinking of that as what's going to turn into the coefficient. You could write it in the other order. I just prefer this. And then square root of 25 makes it 5, and then over 7. Similar, this time it has a 2, so I'm just going to have that 2 out there. And then 45, that's another one with a 9, so 9 times 5. So you can think of this as 2 times, we'll do that, 9 times 5. And then that root 9 would be a 3. And then 2 times 3 makes 6, and with the root 5. So I'm just kind of breaking this down each little step and just keeping that really tidy out front. Let me show you what this will look like with letters, and the letters are actually much easier than the numbers. So back here we have this square root of x squared makes x. Another way of saying this is saying that. So every time we have a square and we root it, we're going to get an x out. And this again is, if I had a square that was x by x, that's x squared, the square root would be the length of the side, or just plain x. So for every pair of x's, 1 comes out. That's the important thing. And again, the reason is the same reason if I'm going square root 25, I have a pair of 5s and 1 is coming out. If I have a pair of x's, 1 is coming out. So what we can do with that, on this first one, not too tricky, square root of 36 would make a 6, and then square root of x squared would be a plain x. So again, every time we see the square root of a square, that's just x. So then what do we do when it's not a nice number like a square, when it's a 7? So now what I need to do is count the pairs, and I'm going to do that in a long, annoying way first, and then show you the shortcut so that you never ever do this way. But here's what I'm doing. So if I figure out how many pairs there are, for every pair 1 comes out. So I got 1, 2, 3 pairs of x. So outside I would have x cubed, and inside I have this 1 left over x. A really nice way to think of this, and you'll see later in other courses where we'll have what's called cube roots or fourth roots, where there's an index on the root. For a square root, there's a little invisible 2 there that we don't write. But what you can use that for is just sort of a little, and again, this is something I'm just doing in my head, but I envision that 2, and I go 2 goes into 7, which is just a quick, easy way of counting the pairs. It's just dividing by 2. So 2 goes into 7 3 times, so 3 x's come out, and then there's 1 left over. So looking at this one, let me write that a little bit bigger. So if we think of the little invisible 2, 2 goes into 20 10 times, so x to the 10 comes out, and then that's a y to the first, so I can't go 2 goes into 1 because 2 doesn't go into 1, so that's that leftover, so it would stay inside. And we have to have a pair, we have to have 2 of them to be able to take a root, so since we only have a single y, it has to stay in. 72 is a little tricky because what you're likely to do is to go 9 times 8 on that one, because 9 is a perfect square, but that 8 still has a 4 hiding out in there. And so if I write that, if I realize that that's 9 times 4 times 2, then I can kind of see that 36. So we're not just trying to pull a perfect square out, we're trying to pull the biggest perfect square out. So for this one, I would write this as 36 times 2 y to the 11th, or at least think that. And then square root of 36 is going to make a 6. Think of that little invisible 2 there. 2 goes into 11 5 times, and there'll be 1 left over. And then this 2 also didn't come out, and then there's our leftover y. So one more time on that one. Square root of 36 makes 6. 2 goes into 11 5 times, so y to the 5th is what comes out. The 2 was left over from the 36, and then that y is left over because we had 11. We took out the 5 pairs with 1 left over. And then this last one here, we got square root of 24x to the 14th y. And 24, that one, and there's a lot of things that 24 is, right? It's 12 times 2, it's 8 times 3, but those aren't perfect squares, so we want to pick 4 times 6 because 4 is a perfect square. So that will bring out a 2 and leaves behind the 6. 2 goes into 14, x to the 7 comes out, none left over. And again, that y is to the first, so that one stays in.